more or less. It's like, well, I was looking at it the last couple of days, so it's fresh in my mind. But like, because you wait 4 months,
right?
It's nowhere in there.
This is a rough draft, or if I get a final copy?
Rough draft.
Okay. Then I won't ask questions on why you have a bunch of white space.
Okay, thanks for coming and supporting the group meetings. Aaron is going to practice his poster, and everyone is welcome to give him quick time. Right? There are printed copies, so please write down your aggressive questions there, so he will be ready to address them in the new version. And next Tuesday, even if you are very unsure about your draw and attendance at any meetings, please try to send. I'm looking at David. Send that. Think like that. Okay. So the floor is yours. We do not have any other agenda, so there is sufficient time to give you card.
So the work I'll be presenting is on Polaron, optical spectra, and excited state dynamics. And specifically, we're looking at Polaron formation and lead halide perovskites, because within the last decade or so, lead halide perovskites have become very popular in the energy fields because they're good for photovoltaics and they're also good for efficient at light emission. And they're easy to process, so they have eventually going to be rolled up, intended to be rolled up for commercial applications. But an interesting thing about these materials is that they are fairly soft compared to other types of semiconductors like silicon or germanium. Types like those are covalently bonded systems, so they're very rigid. So if you put a photo excitation in them, you don't have to consider polaronic effects or interaction with the lattice as much as electron-hole interaction. But in perovskites, it's a different story because they are mixed ionic and covalent bonding. So if you put a charge into them, the lattices will deform, producing large polarons in these systems. And I have an illustration of that as my first picture. So this is the perovskite system I'm working with. And if you put in a charge, which are the black isocontours, so adding an electron to the box, the lattice will have a response, and that's what the little arrows represent. So it's reorganization of the lattice. And what's expected to happen is similar to if you have a defect state or like a dopant in the crystal, you can consider it as like an effective Hamiltonian. So it's a charge interacting with like a mean electrostatic field around it. So it's similar to the hydrogen problem. So you'd expect the polaron to create a bound state and then have a little energy well, which is similar to like a hydrogen well. And so essentially what I'm going to be presenting is optical absorption within the bound polaron excited states. So IR absorption. And then we're also going to model excited state dynamics, considering if you were able to create like a hot polaron. And by that I mean if you could create a polaronic state that had excess energy inside the well, like how would the radiative and non-radiative dynamics of that system follow? And then the most, I guess, provocative idea from this work is trying to get photoluminescence from this carrier, because infrared photoluminescence is a hard doesn't appear in a lot of materials, so if you could somehow get efficient IR photoluminescence from a polaron, that could be would be an interesting idea for an avenue for further research. So that's kind of the intro, the elongated intro. So the methods that we use, we do EFT modeling. So the models consisted of inorganic core. And so the thing with polarons is that due to lattice deformations, I'll back up. So strictly when you think about solids, you think about applying periodic boundary conditions. That's kind of problematic for polarons because at the boundaries, your polaron's extended, like you'll create like edge states, so they won't match up. So what we do is we just create a cluster, what we call a nanocrystal, and passivate it with ligands, and then model the polaron that forms inside the cluster, so you don't have to worry about charge delocalization in periodic boundary conditions. So that's how we set up the model, and then the functional that we use is PB plane waves. It's all done in VAS, so it's plane wave optimized, and then for the dynamics, we implement adiabatic, or molecular dynamics. We do those at room temperature. So yeah, so I feel like I shouldn't be going through like every 5 points.
Would you accept comments?
Yeah.
If I see it for the first time as a way audience, I'm missing the navigation. You kind of declared that goal to generate photoluminescence, and then went to technical details rather than like sketching the pathway. What should be done in order to assess ability of material to use it? How to connect your declared goal with whatever you show results. If you present on with those, it will be more logical and maybe sure.
Right. And I guess that's kind of what I do.
You are doing, but consider audiences kindergarten babies declaring why next steps is needed.
So I have one that is more of a comfort question. So here, some lines only have like 1 or 2 words in, like 2 or 3 words in them. Would it be feasible to like shift this so that these are next to each other, and then you can use the entire column instead of having like the words right?
What do you mean?
Yeah, there, because like as you read that, there's so much that you have to move that it might be uncomfortable for a reader to like actually read it. Does that make sense?
Yeah. I think I tried to do that before, but it's like I can't really push this over.
Oh, I'm more saying like put these next to each other, the 2 images.
Right.
And if you have a space concern, you could move your bromine, chlorine, whatever on the bottom, possibly, so that it doesn't take up the majority of the thing.
Right.
Because that's just uncomfortable. It might not be uncomfortable for other people. I just tend not to like jumping everywhere.
Yeah, I think I was going to redo these images anyway. So I'll be playing around.
Another thing that might be helpful is, I know Dimitri wrote the code that makes the model image, I believe. It might be good to have a white background, because on my sheet, it is not really able to be seen. Like if you look there versus here, when you print it, depending on the printing quality and how colors get transferred, it might be all blue. And then if you start pointing to stuff, people will be like, I don't see what you're pointing to.
I think white's kind of hard because some of the bonds are like gray or white themselves, so maybe just a lighter background. Yeah, because the hydrogens are white. So
Hydrogens are, you could, yeah, but like if you look here, you can't really see anything.
right.
You can see the black boxes, but you can't see it as it is projected. Is that just me, or can you guys see the image well?
Mm-hmm. I guess I can try and play with that then.
But it also might be easier when you blow it up to like this size. Like the
Oh, the
image
whole-
bigger. But yeah.
Question. Yes, so in the introduction, you mentioned you are using computational methods to push the methods. Spectra. What's the meaning of push? Are you just manipulating the data?
Oh, it's just trying to innovate. It's a so experimentalists. Well, as far as I know, it's like people don't look at IR photoluminescence for Polarons. So by push, I mean like push this idea onto people.
Oh, see, when I read that, I read it as you want to use DFT to determine what scenarios cause IR emission, then try and experimentally incorporate that in the synthesis. Not use this as a proof of concept
Right.
to make experimentalists go. So it's kind of weirdly took phrase.
Yeah. Well, I guess when I thought of it, it's like they emit in like the visible, so push from visible to IR. I think that's what I was thinking.
Refocus attention of scientific community from visible emission to infrared emission.
Mm-hmm. That's what I was trying to communicate. So
But our audience will always select worst possible interpretation.
mm-hmm.
So it might just be good to go over it again and make it neater or better phrased.
I have a question. So what's the difference between previous research artists and current information?
It's the same. It's just dressed up a little nicer.
Same?
Mm-hmm.
What you published?
Mm-hmm.
There was Polaron information. Here, large Polaron.
Well, we have to form the Polaron to look at spectra, so it's the same data I've been working on like the past year. For the most part, I think there might be a couple of additions.
It was one major killing question. I was going to ask it after he tries for an hour and then like, what's new?
Yeah, I was thinking to ask the much time is it was now. So that we have to
I think last year at this time I had like half the data processed. So it wasn't like completely finished.
So now it's the complicated.
Yeah, all this data that's in here is published.
And eventually, if time allows, maybe one can add a panel with a little bit of new data.
Yeah, I was thinking about that, but I don't know. Like I would have to remove.
There are limitations only on the width of the poster. But on the heights, no, you can make it down to the ground so the interested visitors can just lay down and read at the bottom.
So you said that all of this is published. The only citation I see of yours is in the normal mode analysis.
They're sprinkled, and so if you look,
Oh, okay.
there's one there, another one somewhere else, one down here.
So why do you mix between using a citation section and then having it directly cited?
I guess with equations, it's just easier to put that there. And I guess if I put more just like regular citations, that would push this box up. It would just be must-based. So it's more efficient just because there's white space.
Do you? So do you cite the same article multiple times?
Shouldn't.
Right, you are ready to be a committee member, and to confuse anyone who presents with scary questions.
Oh, am I being confusing? I'm not meaning.
No, nothing that.
So I don't know how much I want to go into this, but so a rigorous theorist, like someone like Krzyzewski, it's like you would expect when we write out equations to describe Polaron formation, to use all these fancy second quantization methods. So basically you have energy of the electron energy of the phonons, and then the electron-phonon coupling. So the electron-phonon coupling, in some sense, describes the energy or the strength of the Polaron formation. And so to approximate that in DFT, essentially what we do is we compute an n electron system as like the ground state, and then we either add or remove charges, and then let the model re-optimize. And then we approximate that as the electron-phonon coupling, so it's an approximation for the Polaron binding energy.
So the 7 on H Polaron equals HE plus HPH plus HE minus pH. Is that a citation?
Yes.
Is that typically how you would cite that?
I don't know where else to put it. If you put it on the right side, it looks like a power.
So is that 7 for all of this or just that equation?
I guess these forward.
So could you put it in the title? Or would that also be confusing?
Yeah, you can probably put it in the title.
And then do you have a citation for the approximate Hamiltonian? Or is that
I guess I could put my paper there.
all the time?
So that's kind of how we describe Polaron formation in the system. And then technical details. So in perovskites, you have strong spin-orbital coupling because the lead states, or they involve 6p orbitals for lead, so they have large angular momentum. So in DFT, to incorporate that effect, you have to use spinor orbitals. So those are the electronic states that we use to compute the spectra and the dynamics. So moving on to spectra. So we consider two cases. So we consider one case where if you just remove the charge from the system, you create a positive polaron. So that's illustrated with this image here. And so when you compute the density of states, I forgot to mention we computed the spin multiplicity of the polaron as well. So singlet, so that's what these correspond to, singlet, doublet, triplet, the polaron. And so in each of these white spaces correspond to like the polaronic state, and then the colored spaces are the occupied for the electron side. And for each of these states, we use these labelings to help describe the optical transitions in the models. And so the IR optical transitions are shown.
I'm going to open this. Hoping that we permit interactions in the user. For the equations, it sounded really impressive how you explained flow chart by words. Charge in, geometry out. So by modifying the charge of the model, the geometry is responding for re-optimizing bond length. But from equations, it is hard to pull. If you target audience who doesn't have time to focus on all equations, you may design some flowchart. I'm giving not the best example, but you may do something like that, like charge in, geometry out. And then, I don't know, maybe to help readers, maybe not, but suggesting to consider. Sorry for interrupting.
That's fine. So when we compute the IR spectra of the system, so just note they're in wave numbers, so low energy to high energy. So the lowest energy transitions we see are roughly in the same spot for the singlet and triplet, just with different intensities. And actually take that back. The doublet shows a lower energy transition. And that's, I'll get to that in a second. But I guess the main takeaway from this is that the singlet and triplets are bright, whereas the doublet is basically dark. And that's due to, if you considered the occupation numbers in these, so a doublet, for the doublet, it has, the lowest energy is twofold for each band. So a doublet, you remove one charge, so it still has another charge, so another band with approximately the same energy. So the lowest energy transition is basically vanishing. Whereas for the singlet and triplet, you remove two charges, and that kind of opens up transitions between these intrabands.
Wait, why is there a lower one than 500?
Because each band is twice degenerate. So doublet, you remove one charge.
Yeah.
So you still have one occupied, one not. So you still make like a transition.
So the low wave number is a spin flip between the ground state doublet with alpha spin on the same orbital, where it goes a beta on the same orbital.
It's basically zero energy
Okay.
transition. So that's why it's, you see that peak there? And so yeah, that should be the takeaway for both the optical spectrum. So that's for the positive and the negatives. We see a similar trend. So both the singlet and the triplet transitions are relatively bright, whereas the doublet is a reduced intensity.
So why don't we see the low energy transition for the negative?
So I think it's there, but it's, so here I plotted to 1,000.
Okay. So it's
So it's a
there, but it's
scale.
not shown.
Right. So I could include, well, the reason I cut it off is because it's higher in energy. Where like here it starts at 15.
Just double check, and then you can say, instead of I think it's there, you can just say it's there. I just cut it off because it would then make everything else look too narrow.
right? And yeah, that's essentially the takeaway from looking at the IR spectrums. Singlets, triplets are brighter than doublets.
So
And
then,
they show atomic like spectra.
so for your data for getting your transition dipole moment and all of that, why do you put it here instead of in your method section?
I guess it's easier to reference the equation when it's next to the figure when somebody talks about it. That's kind of how I formatted the rest of my poster too.
So then, do you need a method section that has all the formulas, like electronic basis, like you have a ton of white space? I was assuming you were going to add more to that, but if you put it in where you use it, that section be smaller?
I think what I was going to do is just
I'll make
Right.
that bigger.
either put in better figures here and then just reduce the methods down.
What happens if you modify more electrons? Because right now the maximum is 2, right?
Mm-hmm.
What happens if you just remove 3 electrons?
I just see create more and more Polarons. It's likely going to be unstable, so then you have a bunch of like charges interacting.
Can you repeat the question? Can you interpret it?
So Yulan was wondering why I stopped at removing two charges or adding 2 charges to the system. Why not just keep doing more?
Oh, okay. So systematically.
Right.
Like what Sam did with silver.
And checking total energy versus charge, looking for a specific charge with the most potent.
Maybe.
So I guess in this case, we just keep putting more and more Polarons in the system. So it's not, then it goes from like a single Polaron to like a many body type of problem.
So is your system big enough to have a Polaron inside of it?
Mm-hmm. I guess like you can form a Polaron like in one atom spot. So a Polaron can pretty much form anywhere.
I can interpret it in the question divided into directions. One, if one considers a Polaron in periodic solid, then whether size of the Polaron in solid of the same nature is smaller than the size of this cluster to enable the vertical one. So it's a very peak and rigorous approach. Second approach, which Aaron is defending, is any nuclear reorganization from change of total charge can be referred to as a Polaron. It will be not a Polaron in the sense of the bulk, but still same effect of reorganization. It's just two points of view. There is no common denominator.
So I guess moving on to the dynamics of the system. So just to reiterate how to interpret the excited state dynamics for this. So you consider if you add the charge to the system, you would So you could have two cases. You could have a charge give its energy to the left, or dissipate its energy faster than the ions can move. So in that case, you would have a cool Polaron. So that would be like a dissipating energy and then Polaron form. Or you could have in the other limit where you put the charge in and the ions move so quickly that it creates like a hot Polaron before it can dissipate its energy. And so the way that we set up our experiments, it would be the latter to consider. So you consider excited states within the Polaron well, and then radiative and non-radiative transitions within the well. And so that's the philosophy behind it. And then to do all these calculations, we have to be able to mix nuclear and electronic degrees of freedom. And we do that using molecular dynamics. And then for the molecular dynamics, we do some post-processing of the observables into non-adiabatic couplings. So I described the strength of the electron, photon, or the strength of transition between electronic states due to thermal fluctuations. And so the most competitive part of this is we compute it with spinners, which is generally in parts. A lot of people haven't computed non-adiabatic couplings with spinners yet. So from the non-adiabatic couplings, you can use correlation functions to turn them into rates of transitions. And those are illustrated with our red field tensor. They're shown here. So the top figure is for the negative polaron, and the bottom figure is for the positive polaron. And the way to interpret these is essentially state-to-state transitions. So the x and y axis are electronic states, and then the z axis is like the intensity for how fast transitions occur. And the thing to notice between these two is that in both intensity and in, I guess, width along the diagonal, the negative polaron is lower than the positive polaron. It's kind of hard to see with the blue, but essentially what it's saying is that the negative polaron is more screened, or doesn't interact with the lattice as much as the positive polaron.
Is there a reason for that?
I guess I do these separately. So that would say that the negative polaron, there's more nuclear reorganization, so it screens lattice vibrations more than the positive.
So the reorganization is inversely proportional to these values?
Maybe not exactly inversely, but a common theme for polarons is that when they form, they reduce non-adiabatic couplings.
So the positive polaron is less likely to form.
Right, or it's like a weaker polaron. So it interacts with the environment more than the negative.
What do you consider the environment?
So just the phonons, or the lattice vibrations, from within the lattice and from the surface. So yeah, so from state-to-state transitions, we can set up some numerical experiments. So if we just put in a initial condition to propagate dynamics for, we can calculate rates. We can use these red field tensors to describe the non-radiative dynamics. So in this figure, this is saying that we put in and create a hot electron polaron, and when it cooled to, I guess in the literature it's sometimes referred to as the relaxed edge state. So it's like the next highest polaron state before going to the ground state. And so we do those for both the positive and negative polaron. And in this case, we see an interesting contrast in their dynamics. So the positive polarons show the pretty single exponential decay, or there's no like, kinks as it's relaxing, whereas for the negative polaron, you see something that looks similar to like a bi-exponential decay, where there's like there's like a mismatch between relaxation rates. And then I'll characterize more on that in a little bit, or actually it might be just a good time to go there now. And so you can characterize the cooling rates in these systems if you assume that they should decay as like a single exponential. If you plot the dissipation energy, or like the excess energy that you give to begin with versus log of time, it should be about roughly linear. And so we plot these for the two cases. So when it's a free carrier, so not including polaric effects in the geometry, and then with polarons. So the thing to notice here is, so the red and black compare the polaron, positive polaron, and then just a hole without polaron formation. And so we can see that the cooling is slower in this case, and the same trend is shown with the negative polaron. It's just more drastic. So the negative polaron does much less, dissipates energy a lot slower than the free carrier electron. And so that's an indication that the modeling is kind of following intuitive expectation for polaron formation would slow down or reduce non-radiative interactions.
So what is on x-axis?
This figure?
Uh-huh.
I guess dissipation energy.
Okay, and y?
So it's natural log of time.
So it's not 1 over picosecond, but picosecond.
Yeah.
So I guess one divide should be removed.
Yes.
So why do you do the log of it?
So time is proportional to the exponential, or energy to an exponential. So if you take the log of time, then you just have energy. So you make log of time proportional with energy.
Where did that energy go come from?
So it's in the exponential. So it's energy gap law.
And another simple explanation: without log scale, it will be not easy, it will be complicated to see the difference between black, red, and green. They will just fuse together, will be indistinguishable. If you can put all 4 lines, then lower 3 lines will be basically coinciding, because they are like 2 orders of magnitude different from the blue line.
So yeah, that's the non-radiative relaxation. And so we can, so it's while it's in the excited states, another competing mechanism is radiative relaxation. So along the same trajectory, we plot the likelihood that the system will emit a photon, an IR photon, along the trajectory. And so axis is log time. So then these these bright spots indicate that there is intense photoluminescence from these states as it's cooling to the band edge. And then once it gets to the band edge, like this would be considered like the photoluminescence. So this would be like hot PL, and then photoluminescence from like the band edge. So we can see, comparing the negative and polaron, that's, you should look at intensity over its lifetime. Negative gives us a greater number of counts. So that gives one indication that it's a better emitter. than what the positive Polaron would be. And to characterize more thoroughly their luminescence property, we compute the photoluminescence quantum yield from the that we get from our dynamics. So we approximate the non-radiative is from the red field tensor, and then the radiative from Einstein coefficients. So then we can just use the definition of quantum yield is the radiative over some of the other pathways. And what we see is that generally all these systems aren't efficient emitters. The best one we see is at the scale of like 10 to the negative fourth, so it's less than 1% efficiency. But the interesting thing we do see is that there's a pretty wide variance between our best emitter and the worst emitter, because the other ones are at least 2 orders of magnitude, I guess, more inefficient than our negative singlet. And the reason that I noticed that it is improved is because it has roughly 2 orders of magnitude lower non-radiative recombination, while they have roughly the same radiative. So it seems the difference in their luminescence properties is due to this change in non-radiative relaxation. And so to kind of try to figure out why the negative singlet showed slower non-radiative relaxation, we computed normal modes for the system. I guess a reduced version of the system, so it's, I guess I won't get into that, but so that's what I plotted. Over on this side. So what's plotted here, this top panel is normal modes of vibration, and the bottom panels for a negative, positive Polaron display the IR absorption that was shown earlier. And the reason we plot IR is because it gives an idea of where the energy is. So essentially what we're looking for is resonances between the normal modes and the optical transition energies to see if we can find any trend there. And one thing that stood out was for the positive Polaron, the lower energy transitions are in resonance with, I guess I didn't label them here, but these lower mode frequency vibrations, and these specifically come from the perovskite inorganic core itself. Those typically range between 100 and 400, 500 wave numbers. So the positive Polaron is in resonance with the perovskite lattice. Then when you consider the Polaron, its transition energies are higher than what's provided by the perovskite lattice itself, but it also it gains contributions from the surface vibrations from the ligands, which are these CO stretching from a carboxylate, carboxylates, and from the amine. Essentially what we see is that the carboxylates are in resonance with the triplet Polaron, which from the table I showed before was the worst emitter compared to the singlet. So it's off resonance with the singlet, but in resonance with the triplet. And it's confusing why I put this here, but the singlet is in resonance with the bending of the ammonium, but the ammonium doesn't provide any direct phonon modes to the surface, or doesn't bond to the surface. I guess maybe this might help. So if you consider the surface of the perovskite, these are carboxylates, which form chemical bonds. So that's illustrated with the electron density, whereas the ammoniums coordinate to the surface, but they don't directly bond. So they wouldn't provide vibrational modes to couple. So that's why I explained it as.
So in the diagram, in the figure of orbitals in the top, is there any label or any hint how to interpret it? Like if there are 3 carboxylic to lead and 2 ammonia group to iodine, is it just a slice of the surface of the dot, or they are put this way for artistic pattern, or they are slightly different and specify different electronic states?
I guess they're not the same picture.
The same or not the same?
No.
So when they label and explain the difference,
Yeah.
is it different spots or different electronic states?
I guess these, this and this are like the same figure. They just copy and paste.
Okay.
And these two are the same. I guess what you like showed the entire picture, like you would see some electron density on the halide, but there wouldn't be any on the amine.
Okay.
Or the ammonium.
Okay. So basically, for analysis, one needs only 2 first panels with carboxylic and amine. And the rest are just artistic decoration.
Yeah, remove white space.
Yeah, it's completely legitimate. Just
So when I'm talking about the normal modes, that's why I'm saying the ammonium, even though it has like a high peak, like it wouldn't contribute as like a mode that couples to the system because it's not bonding.
But should the dipole attract the Polaron?
So it could be like a spectator, or it is a spectator.
No, but if the dipole couples to the Polaron, then it's no longer a spectator. Because the Polaron is a change in the configuration of the system due to coupling of dipoles to the charge.
Yeah. So I guess
And
well, it's charged
ammonia-
itself,
What is charge?
the ammonia.
So it's NH3 methyl.
So it's coulombically attractive, but it's not chemically bonded.
But for Polaron, the important part is that its dipole is interactive. Right or wrong?
I guess what do you mean by interact?
Like to stabilize the charge, the dipoles are oriented in a way that counter the charge, right? So like if you have a positive charge here, your dipole is pointing this way, that won't be the stable. It will turn so it points to the negative charge, right? So it could be interacting via the dipole, stabilizing the polaron. Yes or no?
Yes.
So
So I guess that would, well, the way I thought about it, it would just provide extra strain,
extra
because
strain
bond, like mechanical strain,
on what?
like the bond.
But you said it's just physical, so it's not really a bond. So it's very, very flexible. So as long as the nitrogen is pointing towards the cesium, is that what it's
It's coordinated to a halide.
halide? as long as the halide is somewhat close, couldn't it still be very easy to move? Which then the dipole would be important. Which then maybe that would be very important for the stabilization of it.
I don't think the charge of it would be more. So if it's coordinated with the halide, like it's going to pull the halide towards it. So that's what I mean by strain. So it's the halide can't.
So you don't think either the chemical bond, the bond or the dipole of the amine group has any effect?
It has a secondary effect, but it's not like it's not directly involved in like computing the coupling, because it's not chemically bonded.
So
it might
in
affect
other words, it's not involved. It's not included in the electronic properties of the states that are important.
And just like secondarily would be, so they can change like the bond angle,
Bond angle between one.
like the. But you consider just a surface without any ligands there. Like it's going to have a different bond orientation than if you.
So if you froze all of your ligands and you just had it encapsulated and then you ran MD, would it have similar results as if you did not freeze the ligands? I'm just curious because since you're like it has no effect, does it really have very little effect or is it like zero effect? But if you're looking at the electronic properties, then, yeah, okay.
I guess I would say the carboxylates on the surface are going to be a lot more.
But don't they interact similarly?
Are they chemically bond?
Did you ever look at binding energies?
Mm-hmm.
So what is the average bond energy for the amine and the whatever the oxygen is?
They're both on like the order of EVs.
So if they're on the order of EVs, then they interact similarly. So you can't say one is important and one's not unless the orbitals that you're looking at extend to the ligand in one case and not the other.
That's what I said.
Right? Aaron exactly shows what your last sentence with
Okay.
graphical evidence.
Not as good.
That's what I was trying to get across with this, or with these pictures.
Those don't have electron density.
This one does. Maybe it might be hard to see.
That's quite a bit easier.
5 times.
Okay. I was just thinking that they were bond and stick. Okay, never mind. It makes sense now. My bad.
So yeah, my interpretation would be anywhere where you have carboxylate contributions in the normal mode, those would be significant, whereas the ammoniums would be, even though they look, there's a big peak there, they don't contribute that much. So the singlet doesn't have any active vibrational modes in resonance with it, while the triplet does. So that's how I explain the 2 orders of magnitude difference in the non-radiative recombination.
So what orbitals of Forde here?
So that would be the HOMO. So that would be like the ground Polaron state.
So is it similarly when you charge the system with an electron?
Mm-hmm. So it's basically the same orbitals, just with some bond elongations or contractions. But the orbitals pretty much look identical.
But when you go to the negative polaron, aren't you looking at the LUMO, not the HOMO?
Right.
So is the LUMO, the electron added system, the same as this?
Top of my head, yeah. It's like it's,
Oh.
I remember I've looked at the data. I didn't see any strong deviations. I usually don't plot them. They look very ugly.
So I'm asking a lot of questions.
No,
Oh,
questions
it's good. It's good. Thank you.
So,
One question. So I guess for this kind of analysis, so basically you have two factors. One, the first factor is resonance potential. The other is using distance between the ligand and the crystal release.
you mean in terms of how strong it interacts?
Yeah.
I guess I wouldn't say distance. I would just say bonding, whether it's chemically bonding or
Hybridization,
yeah.
presence of charge, density in the space between bonded atoms. When we are analyzing the molecular dynamics in structures, the simplest way to assess where two nuclei are bonded is measure the distance. But there is a very advanced chapter that not everyone needs, but it does exist in theory of bond order when analyzes. It doesn't need computation to the level of molecular orders and determine the sp hybridization. The amount of nodes, amount of charge in the space between the bonded nuclei, and if there is a method called bond order that can be extracted either from picture of molecular orders or from any protein structure application. So if one wants to dig deeper into this direction, just put bond order theory from neural name is one Germans and William or and here the very qualitative level Aaron is showing that it's at the level of the high school chemistry. If there is a charge density in the space between nuclei that I suspect that there is a density, then there is a common block. If there is no density, they are good charges that just attract even. And for this purpose, this qualitative analysis seems sufficient to convince that the rigor needs to go deep into the case. Right?
Mm-hmm.
So this is kind of a ease of reader. If you add the drop down 3 lines on normal mode, why do you include the one for the nitrogen, oxygen, hydrogen in that? Why wouldn't you just exclude that? Then you can just say these are the ones that we think have the importance on the Polaron, and you don't have to say this line is a no. Does that make sense?
No, that makes sense. Yeah, I probably should do that. I don't remember why I put that in. Well, I guess if I didn't put it in, it's okay. Someone would think, oh, it's like, it's easy to line them up by your eye. Maybe
Or
I'm trying
like
to dissect them.
you could put an X saying,
Or
oh,
make it
this
red
one.
or something. Different color.
Something. Because if you're not there to say anything, then they're going to say, oh, nitrogen's important. And then you're like, oh, it matches all of the panels instead of nitrogen is not important, right? Because then it gives a wrong impression.
Mm-hmm. Yeah, I could change the color or like the dotting pattern.
maybe put like a key and say interaction, gray, solid, non-interaction, red dashed. And then if you put that, then you can say, then it's easy to see. And even if you don't explain it to someone, they just have to read interaction, non-interaction, and it's done. And then for your photoluminescence, that's intra, not interband emission, absorption, relaxation, right?
Mm-hmm. If you just thought about it as like states in your conduction or valence band, it would be like LUMO to, or LUMO plus 3 to LUMO.
Conclusions?
I was just thinking that. So the main takeaway, we do see signs of Polaron formation from geometry optimization, which wasn't shown here. And from our excited state dynamics, from the differences in the cooling rates between Polaronic and non-Polaronic. Geometries, we do see photoluminescence from the hot Polaron, but they're generally weak compared to, or theoretically they're weak compared to what's, I don't even know if it's experimentally observable. You get like 1000% quantum yield. So it's not within the threshold of what people would want, but we do see an interesting, I guess, surface chemistry impact on photophysics, whereas the surface of our cluster, even though Polarons are expected to screen interactions, that even if there are surface interactions at the edge with a Polaron, it would still highly interact with the Polaron, giving rise to fast non-radiative effects. So the importance of surface chemistry, photophysics.
Do you have any experimental versus theoretical comparison using your method for determining quantum yield?
I guess if you just consider interband.
No, I'm saying the method that you use to determine quantum yield.
Right.
Is there any, has this been applied to a system that has experimentally determined quantum yield so you can get quantitative agreement versus qualitative?
Right. So if you just consider interband photoluminescence, it's like across the band gap, you computed that is like 60%.
And is that comparable?
Mm-hmm. Yeah, experiment they see anywhere from 50 to 100. So
And
it's
for inside the band of the experimental data, I'm not aware.
mm-hmm. Yeah, it's
Which makes sense if it's on the order, if it's less than like a million? No. 100,000?
thousands.
100,000? No, 100,000. Starts with tens, hundreds, so you have to add one to your order. So it's 10 to the negative 4, so it's 5. A million is 6, so it's 100,000.
Okay.
Right? I think so.
So I guess my front digit is either like 1 or 3, but either way, yeah, it's a small number.
Okay, but thank Aaron for 1 hour presentation of what there will be. Do not erase it. We will have more questions. Of presenting things that there will be maybe 5 or 3 minutes to repeat it all for each visitor. More questions. We had a lot, but maybe there are more. Like Kevin may ask to repeat the introduction. Like who needs that sort? I have a question. Continue the question of Kevin. It is not in the poster, but how possible numerically, how far are developments and new results for coexisting positive and negative Polarons? Are there like just numerical cost is high, or there are objective difficulties? Like, is it possible to find optimal geometry when there are both positive and negative coexisting, or excitation from SH to SE in a singlet? Is it possible for an output? And then it's just informal overview what is going on this excited state of this computer.
Mm-hmm. So, yeah, all these data here is independent Polarons. So, typically in experiments, these are photoexcited. So you have an electron and hole, which produce both positive and negative Polaron at the same time. So, depending how they interact, you'd expect them to be quantitatively different, and in their absorption spectra and in their dynamics. But, so I do have data for, I guess, optimal for various occupations of Polarons, or simultaneous Polarons. Like ground state and then spectra and energy and density of states. So basically all of this data for those models. And then for the dynamics, I hit a snag because models generally don't seem to be very stable, or it's hard to get VASP to converge on them. So essentially what happens is if I try to run the model for long enough, the ligands desorb from the surface and it just kind of starts to break apart. Or it's even like...
So technical question, when you do this, are you forcing the occupation to be specific?
Mm-hmm.
And is it not to have HOMO or the highest originally occupied orbital to be half occupied and then LUMO half occupied? Or is it a different ordering than that?
So that's one of the ordering.
Oh.
So it would be, yeah, just putting a hole in the valence band of one occupation in the conduction band. And those ones, I guess those ones are kind of reliable, but I've been looking at other configurations as well. So like, if you had, I guess in my notation here, if you had an occupation in a P band, in the conduction or valence bands, and those ones are very or they haven't shown a lot of progress.
Does the orbital that you place it in change as a function of time?
You mean like whether it swaps?
Yes.
Well, I guess I haven't even gotten that far. It's like they're having trouble like heating.
But heating, you can look at the nature of the orbital.
I guess, yeah. I guess I find problems of like ligands either desorb or it's like they break apart completely.
I guess the reason why I'm asking this is if you have like your unoccupied orbitals are typically anti-bonding.
Right.
Right, so anti-bonding is destable. So if you're in an orbital that initially has anti-bonding character, then you should expect it to pop off.
Right, because you put a hole here, that's, I guess it's not as big of an interaction, but when you add an electron, it's like it's a p orbital from the lead that interacts with the OLD8, and that's, yeah, it just kind of induces flocculation.
That's a fancy word, I like it. Flocculation.
Can we continue asking questions?
Sure.
Interviewing about results that are not shown. It's really cool. So you do have several initial configurations, and for each of them you are trying to do heating with targeting new molecular elements. And they show numerical instability or stop of the job or disruption of ligands. so some catastrophic events. Do you observe how long does it take until catastrophic event as a function of initial configuration? But which of the excited configurations are more stable? You already told that like PH to PE is less stable, but you have more common symmetry.
I guess the S band occupations, those ones are relatively stable. Like I've gotten those to go to molecular dynamics, but they kind of fail, but they jobs fail.
So it's more numerical.
Yeah. So those ones, those could be progressed further.
So you were able to hit them and do several steps of molecular dynamics.
Mm-hmm. But for any of the models that have like a P occupation, those ones just have trouble heating.
Probably as Levi comments, because of the crossing of quantum energies means changing of the identity of the orbitals. When it comes to different configurations that we initially stated. So it probably goes until the first portion of orbitals.
I guess, I don't even know if it's that. I guess it's like they don't converge very quickly at all. And then since it doesn't reach the minimization, it just keeps.
In that CF cycle?
Right. So it doesn't hit like a good threshold. So it just keeps propagating a bad geometry. And it just causes either parts of the model to just kind of drift away from each other.
Okay. So suppose that you focus only on the S curve, SH2SP. Why simulation stopped? Is it like because of lack of convergence, or you artificially stop it when you see disruption physics?
No, it'll just crash in the middle. Like it'll run 10 steps, and it'll just whatever the error is that VASP gives. Like when it's like I can't remember what it's called off the top of my head, but there's like a typical.
Is segmentation fault?
I don't think it's segmentation.
Okay.
It might be segmentation. But it'll just run 10 steps and then it'll just quit.
Is it
self-consistent?
room temperature or recognized room temperature?
Those ones, room temperature?
And you didn't explore recognized room yet?
Not yet.
Okay. It could be a little more stable.
Would decreasing the protein work for
Yes.
stabilizing it? Are
Yes.
you at 1 femtosecond?
It will help tremendously. But it will be like
It would,
conservation work. You win over stability and you lose over productivity.
but if his protectivity is nothing, winning in both would work.
Very interesting.
Can you go to the on So what happened to the Harlequin triplet in 1970?
Well, I think the collaborator, or Helga, he calculated, or he did dynamics for the positive doublet, and I saw that's like that had the worst yield, so I just decided not to do the negative doublet. Just based on the idea that we were looking for photoluminescence, but the lowest energy transition is 0, so it would just,
You would have no emission.
yeah. So you can make good green figures out of it, but they'll just
But the
take a lot
triplet
more.
has higher energy, so it would not work to say that it should have 0 because the gap is 0. So visual to that.
Right. I don't think there's a good explanation. This is just the data that we were able to scrap together. But I guess You could also say that just due to like the normal mode analysis I had earlier, it's like all the positive Polarons have lower transition energy, which overlap with resonance from the ligand or the lattice. So I wouldn't expect those to be interesting either.
Let me play a role as a reviewer. How stable are the results to the change of the function? Did you try some hybrid like HSE or this fancy modern scan functions?
I did one calculation comparing negative Polaron using a hybrid functional, and I was going to put that on here because last year I got an aggressive reviewer asking about why I didn't put any hybrid functionals calculations, so I was going to try to put that on here, but I was looking at those today. I basically saw qualitatively the electronic structure is the same. So we see still has a gap here for this sub gap, which we wanted. I think it was a little wider, including the hybrid functional. And then there's the same characteristic trends with where the peaks were in the states. So in terms of electronic structure, there wasn't that big of a difference for what we're trying to focus on. And in terms of the dynamics, I would just reference them to that Yakimov paper. So there's
Which one?
Alexei's paper. I think he did like a paper testing the dependence of
What's the last name?
Yakimov.
Oh, okay.
Dependence of the couplings on either GGA functionals or hybrid functionals. I think he found that the difference was less than, or it was pretty small. It was like half an order of magnitude difference. So even though you could say qualitatively, the trend should hold, quantitatively you might be off by half an order of magnitude.
In presence of theorists, your saying is very valid. But don't tell it in presence of experimental community. Like the error is small, it's just half of an order of magnitude. Okay. More questions? If no, I think once again. And, if you are making notes and want to help, please consider to submit. Yes. I saw your emails.
I
Yeah.
get those.
Huh?
I tried.
Oh, okay, because it was too hard task for you. Kevin, can we briefly chat?
Sure.
Okay, thank you.